I'll have mic on from here then. Yeah. If any issues with audio visual slides, let me know or put it in the chat box. Thank you very much. And as usual, we record these events and then the recording will be available later as well.
Okay.
Fantastic.
Okay. And then okay.
And I was just telling Leah before the presentation how the real world data side that you guys been building at OMOP and various other data sources, etc. So yeah, hopefully interesting talk. Thank you, Leah.
Okay, thanks very much for inviting me to talk here. Yeah, so I'm going to talk to you today about my PhD work, which is about using electronic health records data to estimate the causal effects of longitudinal treatment strategies in the presence of kind of irregular monitoring of the time-varying covariates. Oh, no, okay, this doesn't work. Okay, fine. I'll just do it like that. Yeah, so electronic health records data provide us with opportunities to answer questions about longitudinal treatment strategies that may not be possible from randomized trials. This requires kind of causal inference methods to deal with the complex time-dependent confounding. Many of these causal inference methods for multiple time point settings require data to be collected at a common set of regular observation times. But in EHR data, however, because these data are collected as part of routine clinical care, the kind of frequency and timing of monitoring or observation of covariates often differs by patient, by covariate type, and also over time, and may also be informative about patients' health status in the sense that more sick patients tend to be monitored more closely. So in practice, often what happens is the kind of EHR data are coarsened onto a kind of discrete time grid for the purposes of analysis. So the aims of my work have been firstly to identify methods to estimate the causal effects of longitudinal treatments using these EHR data in the presence of irregular monitoring, and also to evaluate the effect of this coarsening of EHR data onto a different discrete time grids, and to look at kind of bias introduced in treatment effects. And so the motivation behind this work is in terms of evaluating the effects of different mechanical ventilation strategies on mortality of intensive care patients using routinely collected EHR data from UCLH Intensive Care Unit. So we've looked at kind of both static and dynamic treatment strategies. So static treatment strategies are kind of fixed, defined in advance for all patients. So for example, initiate ventilation within 24 hours of admission and remain ventilated for some minimum fixed period. Or alternatively, dynamic treatment strategies which kind of adapt to the status of the patient. So for example, initiate ventilation when respiratory rate exceeds 30 breaths per minute. And in this talk, I'm going to focus on dynamic treatment strategies because they're maybe slightly more realistic in the context of ventilation, but the methods also work with the more simple case of static treatment strategies. The outcome of interest for us is death, so it's a time to event outcome. And we expect there to be a number of time-dependent confounders relating to the patient's kind of breathing output and measures of how unwell they are in the ICU. And the frequency of monitoring of these variables is really irregular. Like if we have, for example, some things measured every few minutes, some things measured every hour, or yeah, kind of in that kind of range. Yeah, so in this talk, I'm going to describe kind of the observed data structure using EHR data and kind of the assumptions that we need to make. And then I'll describe some causal inference methods that we can use to estimate the effects of longitudinal treatment strategies. And then I'll just describe some results from simulation study and application to ventilation. So this graphic kind of shows what a typical structure of some EHR data in a very simple setting where we just have one confounder and 5 individuals. So the red crosses represent timings of measurements of a confounder LT, and the blue bars represent periods during which the patient may receive a particular treatment, for example, ventilation, up until their event or censoring time. And we can see in this even in this really simple setting, if you try to divide up the analysis time into a set of discrete time points when measurements of the confounder or changes in treatment status occur, you kind of get this really messy grid. And then if we were to try and fill in the gaps in between this to get a really nice evenly spaced grid, we'd have a huge number of time points. And so kind of potentially like computationally not infeasible to analyze, and also we'd have kind of time points where there weren't any measurements, so like a lack of support for the data in the data. So instead what tends to happen is we divide up the time into kind of a set of regularly spaced intervals and then group together measurements falling within each interval. Okay, so to kind of describe this data structure, we can use a causal DAG or directed acyclic graph. So this kind of DAG represents a typical setting where we have time varying confounding, but in a setting where we have regular monitoring times. So we have this confounder L measured at 5 follow-up times, and then a binary treatment status represented by A, measured also at those 5 observation times, and then a time to event outcome, which here is represented by this binary event status variable, indicating whether the event has occurred by the end of each time point. And so, yeah, the confounder can affect the treatment at each time point, but then the treatment can then affect subsequent values of the confounder. So taking just this L4, for example, L4 acts as a confounder between the relationship of A and Y, but it's also on the causal pathway between A and Y5. So we have this problem of time-dependent confounding. So kind of traditional regression-based methods don't work in this setting, or produce biased estimates of treatment effects. So then to think about this setting where we don't, so this DAG kind of would make sense in a kind of cohort study where kind of patients come at regular follow-up times, but this sort of doesn't really make sense in our EHR data, so we have to kind of think about it in a different way. So this DAG is extended to the setting where we have EHR data with irregular monitoring. It kind of looks really horrible, so I'm going to break it down into sections. So now we still have this confounder L, but now L star represents like a true underlying but potentially unobserved value of the confounder. So L star may or may not be monitored at each potential observation time. And maybe, as before, affected by previous values of the treatment and previous values of the confounder. And then we have L, which now defines the observed level of the confounder and can be defined deterministically as being equal to L star for time points where the decision is made to monitor the patient. Otherwise, if we don't have any information, it's kind of equal to the last observed value of the confounder. So these dashed lines represent sort of deterministic relationships. And then we introduce this monitoring indicator variable N, which indicates the decision to monitor the patient at the next time point or not. And because this might be a kind of decision made by clinicians, it might be affected by past values of the confounder, past values of treatment, because patients who are kind of more unwell might tend to be monitored more closely. And then, as before, we have binary treatment A at each time point, and we assume that treatment can only be affected by the observed level of the confounder. And then this event status Y, and we assume that the outcome may be affected by the true underlying value of the confounder, even if it's not monitored at that time point. So just taking one time point from this DAG, if we want to study the causal relationship between A and Y, so between our treatment and outcome, we have to block all open paths, backdoor paths between A and Y. So this first highlighted path shows that we need to adjust for the observed level of the confounder L. So we kind of don't need adjustment for this unmeasured confounder because it's kind of mediated through this observed level of the confounder. However, in this pathway here, L acts as a collider, so we also require adjustment for N, for these monitoring indicator variables, in order to kind of sufficiently adjust for confounding between A and Y. Okay, so yeah, in terms of treatment strategies, I've been looking at these dynamic treatment strategies like initiate ventilation when respiratory rate exceeds R breaths per minute and then remain ventilated for some minimum period S. And we can kind of think about this treatment strategy using this kind of diagram here. So these blue crosses represent measurements of respiratory rate. And for this particular patient, the first time that the measurement exceeds this threshold would be the point that this patient initiates treatment, and then they would remain treated for some minimum period. And then after that, we might think about allowing treatment to follow its natural course in order to allow the clinician to wean the patient from the ventilator when it's sort of appropriate. And this treatment strategy can be represented by this series of decision rules D0 to DK, where each DK represents like a mapping from the observed data onto this binary treatment status, little ak, so either 0 or 1, depending on those kind of variables in the data. Yeah. So then what do we want to estimate from our data? We're interested in estimating the expected potential outcome. So this Y superscript DK, it represents the potential outcome, which is the outcome we would observe if had the patient received the treatment strategy that we're studying, here referred to as DK. And we're kind of interested in the expected potential outcome averaged across all patients. So this is like a cumulative incidence under the treatment strategy of interest. And to estimate this estimand from our observed data, we require the kind of standard causal inference assumptions. So one of these, so yeah, consistency, which says that if the treatment under the treatment strategy is equal to the actual treatment in the data, then the observed outcome and the potential outcome are the same. That just means that we have this well-defined treatment strategy. Then sequential randomization assumption, this is also just no unmeasured confounding. So we're basically saying that like under the set of confounders that we've identified in the data here, the L, A, and N, the potential outcome is independent of the actual treatment observed. So this is, yeah, a no unmeasured confounding assumption. And then positivity, which says that for any kind of combination of subgroup of past covariates monitoring and treatment history, there's a non-zero probability of seeing either treatment state, either treated or untreated patients at each time point. And then we kind of have to make some assumption about the monitoring pattern in our data being representative of that in the target population. Okay, so yeah, I'm going to kind of talk about some causal inference methods that we can use to estimate the kind of treatment, these kind of treatment strategies. So the first one of those is inverse probability weighting. The idea is to reweight individuals to mimic a situation of randomized treatment assignment using the inverse probability of treatment weights. So in this time longitudinal setting, these treatment weights are cumulative weights at each time point K, and where the contribution of the weight at each time point is just the inverse of the probability of the patient receiving the treatment that they actually received, conditional on their past monitoring, treatment, and confounder history. And yeah, we multiply those weights together to get cumulative weights. And then we can multiply the observed outcome by the estimated weight to create this kind of pseudo population in which treatment assignment is random. So then, yeah, we estimate the cumulative discrete time hazard at each time point. So the important bit here is kind of just that we're multiplying this estimated weight by the observed outcome within subjects who are following the treatment strategy of interest and who haven't died up until the previous time point.
There's quite a lot to unpack.
Yeah, I don't know if it's too much math, sorry. But yeah, I think like the key is just that is in this formula for the
Yeah.
weights. And so, yeah, you can fit these models using just like a standard regression
Yeah.
model,
Yeah.
and then predict under, yeah, given the history, and then use those predicted values to kind of get these cumulative weights. And then you kind of take just the subset of patients who are following your regime of interest and average across. You just simply be averaging across the outcome, but instead you're averaging across the outcome multiplied by the weight. Or yeah. And then, okay, this is also too much math, sorry. But like the second method that I've looked at is G computation. So the idea here is that, yeah, under these assumptions you can relate your potential outcome to this series of iterated conditional expectations, where this side, even though it's kind of horrible, the point of this is that it depends only on things observed in your data. So you've got your observed outcome. And then this method kind of works by estimating each term from this big formula, and using the outcomes from each to fit your next. So for example, you start by fitting this model to this innermost expectation, which is just like a regression model for your outcome, conditional on your past up to that time point. And then you obtain predictions from that model by setting your treatment equal to the values compatible with the treatment regime.
So the values would be discrete time point k.
Yeah, at each discrete time point. And then these kind of pseudo outcomes from this model can then be put into the next model. So then you fit a model to your pseudo outcomes from that time point, but this time conditional just on everything up until the previous time point, and you obtain predictions from that model under the treatment strategy, and you kind of keep going all the way until the final time point, and then you can just average over all those predictions, and you get an estimate of this expected cumulative, counterfactual cumulative instance. Yes. And then, so the third method that I've looked at is targeted maximum likelihood estimation, which is provides a doubly robust and efficient estimation methodology. And one of the advantages of TMLE is that it can easily incorporate machine learning models to data adaptively estimate the nuisance parameters, because of the sort of properties of TMLE. And so TMLE is sort of like a combination of both IPW and G computation. So the starting point is to estimate these same weights that we did using IPW. But before, where I said that we fit a regression model, is also the option to fit like a machine learning model to obtain these weights. And then, like as before with G computation, we kind of have to fit these iterative conditional expectations. So the first step is exactly the same as before, fitting this model and obtaining the predictions. But then TMLE requires this kind of updating step to like debias those initial estimates. And that involves fitting a logistic regression to the outcome, with the offset being these initial predictions, and we fit that with weights WK within the subjects following your treatment strategy. And you obtain these updated predictions. And then basically you keep repeating those set of initial and targeting steps for each of the time points, like we did with G computation. And then you find, yeah. Okay, so yeah, all of those methods kind of require you to have these discrete time points of data. And we could feasibly kind of start off with this really fine grid that represents the EHR data, but then we just wouldn't be able to analyze it because we might have like hundreds, if not thousands, of time points. So I wanted to look at the effect of what happens when you kind of coarsen the data by reducing the overall number of time points. So going back to this kind of grid, if we tried to do it on like the finest possible grid, it might look something like this, where you might have like about 100 time points. So instead we might do something like this, where you reduce the overall number of time points. And kind of, yeah, so we might have this time scale K that represents this finest possible time discretization, and then we might alter that timeline to have this new time scale where the time points M are kind of, yeah, require grouping together the measurements in the underlying data. So these measurements of L and A and the uncoarsened data need to be summarized to obtain measurements in the coarsened data. And that might involve just taking like the nth time points or taking some kind of summary measure like the mean of all the values of respiratory rate that were within your particular interval, for example. And then, yeah, important to preserve the ordering so the L's occur before the A's. And we also need the set of monitoring indicator variables. So whereas before those were binary variables saying whether a measurement had been observed or not, now we might think of M as like a say telling us the number of measurements that were summarized within a particular interval. Yes, this slide was just to say that also when we do this, like when we're looking at a dynamic treatment strategy, actually by coarsening the data, we might change the treatment strategy that we're able to study because we can only initiate and stop treatment at times that are kind of compatible with this coarsened time grid. So that's just something to consider. Yeah, so I kind of did a simulation study to sort of like see the effect of this data coarsening. So I simulated a data set for 3,000 individuals according to that DAG that I described initially. So I simulated these values of L star, N, L, A, and Y for 30 time points. And then I generated coarsened data for capital M time points where I varied that capital M for different values. And then I just like grouped the measurements that fell within each interval. So with that, like I took in this setting, in this example, I took L to be the mean of all the measurements of LK and N to be the sum of all the measurements that were summarized. And I looked at this dynamic treatment strategy, initiate treatment when a value of L is observed that exceeds threshold R, and then remain treated for S consecutive periods. And yeah, in this setting, I just used TMLE. You could use any of the methods that I described before. So we're looking at estimating this expected counterfactual cumulative incidence. And then I did this for these 4 different scenarios. So this one kind of represents like this oracle scenario where we could analyze this finest possible time grid. And then this one represents like the more realistic alternative where we coarsen the data to this smaller number of time points. And then this one, I was to highlight the fact that when we coarsen the data, it's easy to kind of lose the information about the underlying irregularity of monitoring of the data. So it might be tempting to kind of ignore these monitoring variables and just adjust for these L's, especially because the monitoring variables we have to generate ourselves in the data set. So this was to highlight what happens when we ignore the yeah, so these are the results. I've plotted these as survival probability, so one minus the cumulative incidence, and the dotted line represents the true values, and then the green lines are these kind of oracle estimates using the uncoarsened data. So there's like pretty good agreement. And then I've added these lines to show the results from using coarsened data to different degrees. So the smaller the M means the coarser the data because it's a fewer number of time points overall. And kind of as expected, like as the degree of coarsening increases, the bias in the estimated survival probabilities increases. So there seems to be some kind of reasonable level of coarsening that might be okay. Yes, and then taking just those results from this M equals 15, I also plotted here the results where we ignore these monitoring indicator variables N, so we just adjust for L, and it shows that you get quite a significantly more biased estimate of survival probabilities. So it's kind of shows the importance of adjusting for monitoring. Okay, and then I've just got a couple of slides on like the application to ventilation. So yeah, I have this subset of this data set, which is adult ICU patients admitted to UCLH between 2020 and 2023. I think that was about 8,500 patients altogether. And then we applied some eligibility criteria to create a subset of patients kind of reasonably likely to, or eligible to receive ventilation. So for example, like we excluded patients who had a do not resuscitate order in place within the first 24 hours, and then patients who had measurements of respiratory rate and FiO2 kind of outside of sensible ranges, and patients who were in the ICU for a very short amount of time, for example. And this resulted in a subset of 872 patients. And our outcome of interest was mortality up to 30 days, which was observed in about 19% of patients overall and about 32% of patients who ever received ventilation. And this plot just shows the day of initiation of ventilation relative to ICU admission. So over time, cumulatively, up by day 14, just under half the patients in this eligible set were receiving ventilation.
Quite a normal population, isn't it? 30-day mortality is not low.
Yeah, I guess because I excluded quite a lot of people who were probably, even still, I think it was quite difficult to get this kind of, I guess it's a reasonably heterogeneous cohort. And I think the initial idea was to subset also on COVID patients to kind of try and get a set of patients that were maybe more comparable, but then the number of patients was really small and it sort of didn't really work. So yeah, it's a bit caveated that. And then these are some estimated counterfactual cumulative incidence curves under these two different treatment strategies. So this orange one is the one I described, this dynamic treatment strategy, and then I'm just comparing against kind of a simple static treatment strategy of like initiate ventilation on the first day of admission and stay, I think it was remain ventilated for like at least 5 days. So yeah, there's not a huge amount of, well, there doesn't appear to be a huge amount of difference in the treatment strategies, but what I wanted to compare here was the coarsening the data. So this data on the left set on the left was every time point was a single day in ICU. So we had 30 time points, and then this one is every time point is 2 days. So we had 15 time points, and you get much smaller like confidence intervals.
I mean, the confidence intervals overlap, but with the yellow line seem to have flipped.
Yeah, I mean,
around day 14 for both data sets, right? But between the different spacings. So 24-hour mortality is higher. This is how I read it. Correct me if I'm wrong. The mortality is higher with a dynamic strategy at day 14. The step up around day 12, day 14, where that's not the case in 48 hours.
Yeah, I mean, but in theory, these things should be the same because we're kind of trying to estimate the same things, and it just shows that you kind of, I think, how you format your data just really makes a difference in terms of what you're estimating. And I think that step is often ignored because like, let's use these really
and it's a lot noisier because there's a lot less patients. So as time goes by.
There's sort of a trade-off between what you're able to work with in the data. Because in theory, we would like to maybe study an even finer grid because people can initiate ventilation at any point.
True.
But yeah, I don't know. You probably have much more interesting things to. There's also maybe not sufficient difference in these two treatment strategies to look at. Like maybe it might be interesting to think of some other. Okay, yeah. So that was kind of that was it in terms of the work, and then so I looked at different methods, causal inference methods for estimating longitudinal strategies in the presence of irregular monitoring, and looked at this effect of coarsening of data, which introduces bias in estimated survival probabilities, and that bias kind of increases as the level of coarsening increases. So in theory, we should aim to choose the smallest level of discretization that's computationally feasible and that shows enough kind of support for the data at each time point. And the choice of discretization may also benefit from clinician input. There may be kind of obvious time points when like in this ICU setting, even though we have measurements every minute or so, in reality, like maybe the timings when kind of ward rounds or shift patterns happen may be kind of indicative of how often maybe changes are likely to be made in the patient's status outside of like real emergencies. And then coarsening of data may mask the underlying irregularity of monitoring of the covariates. So it's important to adjust for these monitoring variables N, and in the coarsened data, those variables could be represented by, for example, the number of measurements summarized in each discrete time interval. And the coarsening also affects the treatment strategies and therefore the estimands that we're able to study. So it's worth kind of taking into account how the assumptions change under data coarsening. Thanks. These are some references. And then, this is work with my supervisors, Ruth and Carla, and funded by an NIHR grant. And this is a QR code to a preprint. This work. Thanks.
Thank you. This is really cool. it's a lot that I need to sit down and sort of think. But I have a couple of questions. So it seems like the coarsening or the K selection is quite key here because it can affect how the estimate and treatment effects work out, right?
Yeah.
And you ideally want as smaller K as possible. But if your data I'm just thinking this respiratory rate is hourly, but you want the K lower frequency than that, how do you solve that? Because those are other covariates which you mentioned are important to keep track of, right?
Yeah. I mean, you can own, yeah.
Would you be limited by the resolution of those variables?
Yeah, exactly. You can only go as kind of as fine a grid as that. But if it yeah, I think it sort of depends what the underlying assumptions are. If the measurements aren't there between grid, like between timings, then if it's safe to assume that that's because they really weren't even measured and then they couldn't have been used to inform treatment decisions. So you sort of don't really need to worry about it. But it's just because the data is so messy and the measurements don't align neatly that even if they're only every hour or two, once you kind of divide up your time and match it along patients, you might end up with an even finer grid, but with missing measurements in between. So it's, I don't know, I think there's kind of a...
Is there sort of a methodological solution for that? Because I can imagine on ICU, someone might go for a CT scan and their observation might not be documented in the time they're in the CT scan or in operating theatre, and they may come back and that event and that pause might actually result in CT look really bad. Let's just shoot this person.
Yeah, I don't know, and that's like something I don't know too much about because I don't know kind of as much about what's happening like
and how do you tackle like I'm thinking from a simple I'm an applied statistician, I'm not like you said, I'm approaching from a non-expert point of view. So for example, if you're looking at mixed effect models, so they handle through the random effects, how biases between different clinicians who one might want to intubate early, one might want to delay. So those are handled by the random effects. And you look at how the random effects are to see the heterogeneity almost. Similar, does this causal effects kind of take care of that in a way, or?
I don't know. I mean, maybe there are ways to fit those kind of random effects models within these causal frameworks, but I don't know anything about that. Yeah.
Just a question on when coarsening to different time points and you choose how you want to represent the multiple measurements in between.
Yeah.
Is there a particular approach or is that guided by maybe what makes sense? Is do you systematically measure? Do you counter-see?
Yeah. Well, in my simulation, I tried lots of different options. Like I thought that there might be a big difference. Like I thought there might be a difference if, for example, you took the sum of the measurements rather than the mean, because I thought that might capture a bit more of the variability. But in my simulation, it didn't make a huge amount of difference. But I think maybe what's based on kind of like a combination of clinical judgment. Maybe, for example, like taking the maximum value might make sense in cases, especially where you're looking at dynamic treatment strategies, where you're saying like initiate the treatment once a value is observed above a particular threshold. Because if you take the mean, then you might be losing that point at which it goes above a threshold. So I think, yeah, maybe it will depend on the variable and on what you're kind of using it for.
Does this approach does it allow sort of I'm thinking again approaching from a more simple kind of approach that I understand, which is more like joint modeling and so on, which allow individual treatment biomarker trajectory, for example, respiratory rate, and then you can do point prediction with certain confidence interval. Does this sort of approach allow, is it all every treatment effect in your estimate, or do you allow individualized treatment effects?
I don't know if maybe there's like a distinction between like prediction. Are you kind of talking about prediction models or
more like I guess sort of if you fit a normal linear regression, you got average treatment effect more or less, right? Like, so is this the E here is the average treatment effect, not individualized?
Yes, that's true. Actually, yeah, that's true. What we're estimating here is an average treatment effect, or I was just doing one part of that, which was the average effect of one treatment. But yeah, you could then subtract two things. So this work is focused on average treatment effect, which are a lot easier to study in a causal setting. Then there's also loads of work on like conditional average treatment effects, which is maybe, but actually the like maths is a lot harder in terms of, or it's quite a lot harder to. And but I went to this conference, this causal inference conference a couple of weeks ago, and there was loads and loads of work on conditional. But yeah, it's really interesting. I don't know that much about it.
This might not have been included in what we're sort of looking at, but did you look into whether there was a difference between like IPW and G?
Yeah, like not so I've done kind of two separate bits of work, and I the paper actually has like compares IPW decomputation and TMLE, and I think especially when like you kind of change some of the parameters. I mean, TMLE seems to work better in the settings where, because it allows for, with TMLE, you have two chances to get the model specification right, because you've got your model for your weights and the model for the conditional outcome. And theoretically, you can misspecify one of those two models, but still get the correct estimate of the so sometimes it shows better performance, but it's also like a bit more complicated to implement. So I can see why people don't use it as much. And often requires, especially in this longitudinal setting, you could do it by hand, but it's really fiddly. So often requires like a specialist packages and stuff to, but yeah, you tend to get like wider confidence intervals with IPW versus G computation, but G computation also has more potential for bias, because you've got a lot more, you're kind of fitting more models that you have to get right. So that's also kind of a known like
people use it as sensitivity analysis, do you think? Was that the...
Yeah, I think, well, like it was kind of nice if you have the time to run all these different methods, but maybe it's a bit scary because you probably get different results every time, and then you're like, well, which one is closest to the truth? I don't know, unless you're doing a simulation. I guess you just don't really know.
Has anyone got any questions from online? Hello. In the meantime, could I ask all of you to fill this feedback for Leah's talk today? I have a question which is about application, because we have awful lot of longitudinal EHR data, and trying to answer causal type questions would be very interesting, from drug treatments, all sorts, and this could be scaled to many different specialties in many different settings, you know, from say diabetic HbA1c monitoring to steroids that we discussed about. What do you think are barriers in sort of uptake? I mean, I have my views about it, but I'd like to hear as someone who's done this as a PhD.
I think like access to data is really hard, because I think even
wish we have that. So,
I guess matching up the people with the skills about the methodology and then the data is often
I think from my dabbling kind of approach, I find it really hard to if I'm fitting a simpler or more, I can visualize it and I can like, yeah, that makes sense. But I totally feel lost whenever I try even simple causal methods. So obviously that's why I'm not an expert at all. No, so that's really methodological challenge. And the other thing is trying to communicate that with stakeholders. Like, we are a pretty nerdy crowd, but if you're talking to stakeholders of a patient, that's quite challenging to make it accessible. So I wonder if you find those as well.
I don't have like enough experience with that. I think I've only been on the very like far end of the so I would be interested to know more about that myself, because like just accessing the data for me was really hard and took a really long time. And even once you have it, like sometimes, for example, with this work, I have to work with this data in this kind of horrible
was going to say, what tooling are you using?
It's like the UCL Data Safe Haven, and that's where my data is stored. So I have to kind of log into that system, and
It's Steve's UCL TRE, so trusted research
like
environment.
OMOP data that I kind of, and also just having a connection between because I kind of just got given this data without really anyone to help me, like
the variables and
so just like getting the code list for the things that, and and I guess they maybe change over time, because I have this list of codes that people had previously used, but I wasn't finding the variables that I was expecting to find, and then it turned out they'd been coded differently, and I don't know, I think that kind of stuff is really
so
hard
if you could do this prospectively, and you have this entire hospital network and this data, and you have lovely data engineers who can tell you what variables mean and can do the wrangling, what would you do differently?
Like right from the outset, I think I would just have kind of discussed it with you, because there are lots of decisions that I made along the way, and just in getting that data set into a nice format that may have been a bit wrong. I don't know, because I'm not sure. So I think like just working all the way through the process with people, and also, I mean, this was a bit limited by the number, so I think it would be really nice to have data across different hospitals, because I think that's kind of
I think
problem.
it would also be interesting to see different diseases. So, for example, some diseases the clinician might not even consider intubation.
Yeah, exactly, and
some do more.
Yeah,
we don't know that latent variable in this
exactly, because there are like 50% of the patients who don't ever receive ventilation in that set, and I don't know whether maybe they shouldn't be there. It's really difficult to say, because like we tried to apply these sensible eligibility criteria, but it's
and also a lot of the decision, for example, for intubator or not, is documented as free text. So if we can digest that to pass some clinical intent score or whatever, something like that, that'd be interesting as a variable.
And this is a more rudimentary question, but if you were trying to adopt a new modeling approach, and maybe some you mentioned, how can you what approaches are there to check against model list specification, any assumptions that maybe aren't in place? Do you have any general
I should have a good answer. I'm just trying to think. I mean, I think, well, there is lots of work on like unmeasured confounding and ways to kind of, so they're sort of using like proxy variables and stuff, and there are kind of different sensitivity analyses documented in the literature. I don't know lots about that stuff because it's not been like a focus of my work, but the kind of no unmeasured confounding assumption is probably the biggest one that you want to try and like the positivity assumption is something you can check like with your own data, because you kind of can look at the balance between treated and untreated in each kind of combination of different so that's something that you can try and look at, like, and then if the weights are really huge or something, that's kind of an indication that you've got like near violations in that assumption. But there are probably other people who know lots more about this kind of stuff.
Is there any way that anyone could reproduce what you've done with other data sets around the country? Like how reproducible is it?
I have been trying to I have been putting, because I've just submitted this paper and I've been putting the code that I use for it on like a GitHub thing. So just for the simulation, which is kind of obviously a very simplified version where you have like one confounder, but it is there, or it will be there in a nice way soon. And so that was sort of, and I think that's also a big like barrier to.
Absolutely.
I found it so hard to understand how to implement some of these methods, especially TMLE.
If you find it hard doing the PhD, ask Walter. There's a question from Benjamin Pierce. Thank you, Ben. About TMLE plots. I'll read it out so that everyone can hear. The TMLE plot. This was for only patients who administer invasive mechanical ventilation. Is that correct? And if so, that's for 40% of the cohort.
Yeah, that's kind of true, because the way the method works is like, well, the first step where you fit that initial model of the outcome, that's fitted in everyone, but then when you do that updating step in the TMLE, you fit that second updating model in just the set of patients who are following your treatment strategy. So those people who never received it wouldn't ever, well, they are included up until the point that they deviate from the treatment strategy that you're interested in. So in a like ventilate from day one, those people are excluded right from the beginning. But in a dynamic treatment strategy, they could be included up until the point
The
that,
last key.
yeah, that if their measurement of respiratory rate hadn't exceeded the threshold it needed to exceed to initiate treatment. But yeah, that's sort of broadly speaking true. So yeah.
Does that answer your question, Ben?
I think so, and thanks for the explanation. I need to read it again and fully digest. I think I just need to sit down with the paper probably with a bit more time to understand when patient follow-up is sort of valid for this, given that it looks like only 40% of the cohort were offered any kind of ventilation, only up to maybe 14 or 15 days. But yet the cumulative decease rate seems to be increasing throughout the 30-day period when it's for patients only to have been offered ventilation. I'm just losing that plot, but I'm sure it's on me. I just need to read the paper carefully.
I was thinking same with that 14-day step, because what looks like, I mean, the confidence intervals overlap, but there looks a flip between the just intubate group and intubate when rest rate is above 30 group, you know.
I guess, yeah, these numbers aren't going to align totally with these, because these are like because these are kind of crude estimates from your raw data. And these are once you've adjusted for confounding essentially through the TMLE method. But it will be the case that you kind of by this end time point you've actually excluded a lot of people because they don't comply with the treatment strategy up to that time, and that is a limitation with doing these longitudinal analyses, especially when you try to have lots and lots of time points, because like say your treatment strategy is always treat, you might have somebody who is treated almost at every time point but apart from one, but at a certain point when they deviate, they're kind of removed from the analysis because they're no longer compatible with the treatment strategy. There are like certain methods that can sort of kind of utilize that data, like with IPW, you can, rather than just estimating it within people who are following your treatment strategy, you can fit like a marginal structural model instead that you fit with the IPW weights, and then you're kind of borrowing off data from but it's a bit harder with TMLE to do
it's a
that.
bit more involved, that method. Yeah.
Although,
Cool.
Thank you.
Yeah, very interesting. Any other questions online or in the room? No.
thanks.
Thanks very much. I'll stop this call. Please, could you do some feedback for Leah, please? Thank you very much, and see you next month.
Thank you, everyone. Thank you.
Thank you, Ben.